Hello, my name is Zachary Jones, and I am a performance and kernel engineer at Verizon Media Platform. Today, I would like to talk to you about performance analysis of XDP programs. As a little bit of background, Verizon Media Platform is a content delivery network, and the performance and kernel engineering group looks to improve the efficiency of these servers spread across the edge of our network. For us, XDP is a tool that allows us to add optimizations into the Linux kernel to improve the efficiency of those servers. For those unfamiliar, XDP is the Express Data Path and is a BPF-based high-performance packet processor. Because it is in the Linux networking stack, it does not require specializations, such as re-implementing the TCP/IP stack in user space. For higher performance, it does require driver support, but many NICs have driver support today, and the community is continuing to add support to more drivers on an ongoing basis. BPF is the Berkeley packet filter and is a virtual machine-like construct that allows for safe execution of arbitrary bytecode. Recently, it has been extended, the BPF language has been extended to allow more functionality, such as XDP. However, it's existed for many years before that. For anybody that's ever written a filter for a TCP dump, that actually gets compiled into a BPF program. For those that would like to learn more information about these technologies, I provided a few links here. One last piece of background motivation is, how did I get here? And like many good problems, it starts with a Friday afternoon engineering discussion. In this case, a few of my colleagues were having a discussion about when and whether to use hash table or array-based BPF maps. And after some discussion, they decided to ask for my opinion, after which I went off for several months to do some research and came back with a very conclusive answer of, it depends. So now we'll fill in a few months of details to come back to that very conclusive answer. We'll start out with why this is a hard problem. We'll then go into the approach that we come up with doing the performance analysis. We'll talk about some of our outcomes and then our ongoing work. So at the point in the time this conversation had occurred, we'd already started deploying XDP code into various test environments and into production. So in order for me to be able to really understand things, I decided to start with a kind of foundation to begin with. So in this particular graph here is a test environment that we have where one server highlighted with the box there running an XDP program, while the other servers are running the traditional kernel code. And in this environment, it runs production traffic, but it's a small environment so that we can safely control the amount of load and minimize any type of variations. And in this particular case, when we increased load into the environment, you can see a clear separation in soft IRQ utilization between the test server and the test of the XDP code versus the traditional kernel code. However, as I looked at it, I began to wonder, is it too low? And in particularly, some of the valleys that I've highlighted with the arrows are actually running CPU utilization that's within the range of that server before and after the increase to traffic, which is not the same scale and behavior that the rest of the control group has. And so this was not something that I could definitively explain. I had potentially some theories, but nothing that was concrete. And I think that's, at this point, it's good to talk about a concept that Brent and Greg introduced called active benchmarking. With active benchmarking, you analyze performance while the benchmark is still running using other tools. You can confirm that the benchmark tests what you intend it to and that you understand what that is. In this particular case, I did not have the understanding. And so I laid out a plan, an investigation to gain that understanding. So I went back to our test lab and created a test using a synthetic load with a generator that we had a good understanding of its abilities and characteristics. So using this load had a certain configuration for it, 20 million, going to generate 20 million packets per second, and then configure a test system in a certain particular way, this with key of having 20 receive side scaling CPUs. And the critical piece of data that we got from that is for 1 million packets per second on each of those receive side scaling CPUs, each CPU had 1% soft IRQ CPU utilization. Now, when we break that down, that turns out to be about 10 nanoseconds or 30 cycles per packet. That 30 cycles had to run driver code and our XDP code. In our XDP code alone, there were 10 key tasks that were being performed. So that roughly leaves about 3 cycles per task. And when you start thinking about 2 to 10 cycles to load just L1 and L2 cache accesses, and the fact that we have to think about interrupt handling, receive side cleanups in that path as well, this starts to become a very unrealistically low CPU utilization. And I think this is also a point to talk about, before going through this investigation to gain this understanding, we had been casually or passively benchmarking the code in these environments. We had data, and that data was good to be able to functionally validate that the XDP code was running successfully. However, we lacked information in understanding what was going on. And, that transition of turning that data into information is what, was really a result of that active benchmarking. And the information gained was time accounting turned out to be a hard problem. So the way that the Linux kernel keeps time allows for the CPU utilization metrics reported by tools like Systat to be skewed. To further complicate that matter, Linux has multiple ways of keeping track of time. And different Linux distros will use different default accounting methods. And each one of these methods has a different impact to the kernel's perception of time. It's also key to highlight that the XDP code that we have been evaluating has been running in the soft IRQ context because time precision in this environment turns out to be challenging. Certain count methods can miss entire soft IRQ periods. Other methods that track transitions can add overhead, which reduces skew but still has skew. Also the C states that allow for processors to sleep cause some of those inaccuracies. So turning on idle polling can help to mitigate those. And also, you can look at instead of using the kernel's timekeeping, there's also hardware performance counters inside the CPUs that can be used for this reporting as well. Now, this is not a talk about CPU utilization, but I do want to highlight that 1% that I saw in the lab when I went and turned off the C states and used idle polling turned into 60% utilization, which going through that list of items makes a lot more sense. And this, and it's good that we found this early on. It was a good reinforcement for active benchmarking so that the work that's built on top of this will have a solid foundation. I do want to highlight that XDP and BPF is fast. I don't want to take away from that. But in this case, it was not 30 cycles per packet fast for our workload. I do also want to highlight that the performance of XDP and BPF does come at a cost. BPF code is jitted and inline aggressively. This leads to call graphs or flame graphs being flat. And if you happen to work on a system that has a kernel pre 4.16, there actually are no function calls. XDP programs also exist within the limits of the kernel's network and interface, the new API, and it has its own set of factors that limit the scaling in performance. Also, BPF programs do not have kproc hooks. However, in newer kernels, there are support for fentry and fexit BPF programs and the ability to profile that can help with that piece as well. But this is, a lot of words to really say that BPF is a moving target with lots of features being introduced continually. So now we've talked about that, we'll go into our approach for XDP performance analysis. And particularly in this talk, again, I'm highlighting the performance of the BPF code for inside of XDP. This is not a talk about arrays and hash tables. We already know my answer is it depends. But that was a good springboard to get serious about doing the performance analysis. Also, we will not cover various XDP-based XDP adjacent tune-in options, such as things like tune in the CPU affinities or receive side scaling or packet steering. We will mention some of these tune-in efforts at times as they tie into things core to the code. But I really want to focus, a core approach to the analysis of the XDP code. So 3 components to this. The first being an analytical budget time measurement, where our goal is to really understand where and how the CPU time is being spent and understanding how much time we have to work with. Also want to look at the building blocks, so creating a set of micro benchmarks to understand the path length cost of various helper functions and using the data structures that BPF provides us. And lastly, we look at the instruction level sampling and annotations to be able to look at code and to be able to find hotspots in function call in helpers or in branches inside of the code. So first, in the analytical budget time measurement, this relies, purposing the flame graphs to visualize what the CPU is doing. The goal is to be able to see spires for various parts of the system, such as the XDP code execution, the network and driver code, or network and API code, and also if there's any other code running on the CPU. To do this though, we can't just use, there is some tune that has to go into the environment. We have to use turn on the idle poll to turn on the idle polling and not use C states. And then also in this particular case, I'm looking at the performance of a single CPU that is one CPU that's doing the receive side scaling. So here is a flame graph. These are very nice. You can see there's lots of information that is packed in a single image. So here I've highlighted in several boxes kind of support code that's going on. On the right side, we have the network and the new API code and the driver code. And on the left side, we have some various housekeeping and system activities. In the box I've highlighted here, this is actually our XDP program running. You can see there's, has much less height to it. And when you do see kind of the layers stacked on this is where we are calling into some of the helper routines. And then lastly, the key piece of turning on the idle polling and not going into sleep is it actually allows you to visualize the idle time that is spent on the system. So in this particular case, what we're measuring is about 25% idle CPU time, which is kind of the budget that we can have to add more complexity to our XDP program. Now, I said in the previous, the packet rate here is what we're calling our max input packet rate, and this is what we want to be kind of our sustained packet rate without having loss. And so to adjust that pack, things that we can do to change that time is look at things like some of those tune-ins, such as interrupt coalesce and receive side scaling. Also, in terms of helpers, things like RCU cleanup and other helper things, there are kernel config options and command lines that we can look at to help achieve that as well. And also, as a side effect of this, when you look at the driver stack, you can actually compare to see if different drivers consume different amounts of time as well. So moving on into our next approach, we have MicroBenchmark in our building blocks. So the kernel provides a BPF prog test run command to the BPF syscall, which allows for running the same piece of code over for multiple times for testing. And I provided an example here of how to use the BPF tool to do such a test. Alternatively, which is a path that we ended up using, was we actually built a test harness using various BPF helper functions to do the same thing. And in this case, we're really, what I'm going to measure is the difference between two tests. We perform a test of just a simple pass-through program that does, you just call the function and return success. And then we call another program that does something of interest, testing a component or a helper. And then, the data we'll report is going to be the difference between those two runtimes. So, I started this off with arrays and hash tables, so I thought I should at least provide some data that shows some of those differences. And here we have a graph of on the left of doing updates and on the right doing lookups. And so you can see the various differences. And for pure path length, arrays are more efficient than hash tables. But again, it depends. Sometimes hash tables are needed based off of the memory that you need or complexity of what you're looking at. So it is, that's out there. But also looking at things like the per CPU arrays and per CPU hash. If you are doing something across multiple CPUs, and if you have contention, if the data is not going to be shared or is going to be shared, these are things to look at. That sometimes, the sheer overhead of doing a per CPU array or per CPU hash lookup is more expensive, but you don't have to deal with concurrent accesses with them. And that's good. That's good to point out because, the tests I'm running are single consumer producer models. So there's no contention that actually occurs. So we're just seeing like raw path length without any of those more complicated interactions. So you have to be careful of that when you're looking at these measurements. And again, arrays or hash tables, the answer is still it depends. Talk about some of the data structures, but I also thought it was good to look at some of the comparisons of CPU architectures. So here I have several using helpers such as getting a random value or looking up the time, and you can see in general that things are either constant, or relatively constant across our generations. We generally try to maintain, we get roughly the same processor speed out of all of our generations. But something happened with our 4th generation CPU in this graph where it actually has a significantly lower cost to get the current time. So some kind of architectural change happened with that CPU that improves that time lookup. On the right-hand side, we have a graph of using the BPF tail call. And interestingly, the 3rd generation CPU that we have, or generation 3 CPU that we have, is abnormally low. And so it's kind of thinking like what makes that system unique in that case? And that really turns out to be, again, this is like triggering that active benchmark and thought in my head of making sure to explain that. And this is a result of a configuration difference, which happens to be that generation 3 system had been configured to disable the speculative execution mitigations. And we actually enabled them. Now you look at the graph, and it makes much more sense. So lastly, let's dive into instruction level sampling. Here we are going to use the annotation feature of perf. So perf allows you to look at, one of its options is to look at the assembly code inside of a function and look at the utilization of each one of those instructions. The annotations actually allow you to take C code from the kernel and put it in line so you can see which assembly code belongs to which line of code. The profiler looks, at x86 assembly code, the BPF code is goes from the virtual machine language to x86 code. So there's several layers of discrepancy between the actual BPF-C code and the actual assembly code. However, the BPF type format, BTF annotations that can be added to code allow for perf to actually inline the BPF-C code for those functions. Now, it does require a fair number of prerequisites today. Hopefully, in the upcoming years, these prerequisites will be satisfied by, distro built versions of the perf tool. And in use cases, it's fairly straightforward once it's built with the right dependencies. You just use perf record with your favorite set of arguments, and then you can either look directly at annotated functions with perf annotate, or if you look at a perf report, you can go into any function of interest just by pressing the A key. So here is a example of a trivial function looking at the annotated code. And left and right, this is the same trivial function. But there's one difference that we are going to analyze and understand what the difference is. So in the current arrows, I'm highlighting that we're doing a lookup in an array and then comparing its value. Now, if you look at the bottom three arrows, we actually have the same line of code repeated. So what's going on here? We're actually seeing each kind of the breakdown of that if statement. The first piece is we're testing to see if the variable v is null. We are then doing, the second one highlight is doing the pointer dereference of v. And then the last one is actually doing the comparison of v to the test value. So now moving on, so now we've changed arrows to actually highlight the difference of what's going on. The left side is looking up a valid index into the map, while the right side is looking up an invalid index. So we can see that what ends up happening is when you look up an invalid index into a map, you get a null value so that you don't want to dereference it. Thus is why we do the null check. And so this ends up being why the bottom arrows are at different locations. On the left-hand side, because it is a valid dereference, or it's a valid pointer, we actually see that the hot point in the sampling occurs with actually doing the pointer dereference, while on the side with the invalid lookup, we see that the null test is causing it to jump early down to the function exit. So again, like this is a fairly trivial example just to highlight how you can look at the branching differences. But you can imagine with more complex code, you can see if a particular branch is hotter than other branches, or to just find if some particular call or path is hotter than other areas, so that you can look to see which pieces of code are more important to go after and optimize first. All right, so now that we've gone through the approach, let's talk about the outcome. Does this methodology work? And by XKCD standards, I think yes, because I didn't have to consult a flowchart about this. However, we are running XDP accelerated code in production POPs today. And we are doing that with a level of confidence. We're continuing to develop this and being able to achieve increased efficiencies on those servers. So, I would like to say yes. I didn't include any charts because, again, this code, this talk has been focused on the analysis of the XDP programs. But, in reality, this methodology was being used in conjunction with some of the tuning up, the XDP adjacent related things such as RSS tuning, RCU offloads, things of that nature, which allow us to achieve higher pieces. So it's hard to, untangle those two from our performance results. but together they allowed us to continue forward on this path. And in addition to that, as a side effect of building these, we now have a new way to evaluate our systems. We can look at the cost of the driver or understand how CPU architectures can change and impact these runtime codes, so that we understand as we build out new systems, what do we have an increased budget or a smaller budget for these XDP programs, and plan accordingly for our development process. And again, this has been a good exercise of taking a complex problem and breaking it into smaller chunks. Our approach allows for to target various areas, understanding how time is spent, understanding the cost of using various building blocks that we have, and also how to look for our hot spots to go after those. And lastly, just to hammer it home, active benchmarking has been a key for our success. We're going through this every day now. We're making we have a confidence that our measurements make sense. We're doing we are verifying that testing that we do is being measured, is being measured and is intended to do the things that we want it to do, and that the results, and that we understand the results, that the data that we get back from this is actually information, enriched information that allows us to make good decisions. And also, this is, as you've started to talk with, BPF is a rapid moving target. Recently, BPF struct ops has been added. The first implementation of that is being able to write a TCP congestion algorithm inside of BPF code. Also, there's the Linux security module hooks that allow you to build various monitoring or control systems with BPF. So, hopefully this XDP is not the only area where we will be doing performance analysis with BPF. That as we build other BPF programs in various parts of the kernel, this performance analysis approach will map to them as well. So lastly, some of the ongoing work, BPF, the network and stack are moving. There's lots of things that are going on. There's additional helpers. There's more data structure types. Our current, as I mentioned earlier, XDP code runs in a soft IRQ context. The 5.12 kernel introduced a K-thread-based RX networking approach, so that will be interesting to change with those settings to see how that affects how we measure the system and what challenges or opportunities that presents. Also there's the BPF F entry and F exit hooks. How can we leverage that for XDP programs? And also there is profile support built into BPF tool now for some low-level understanding of programs. Also, since we do have this tool for understanding the various helpers or other things that run on the system, running on a CPU on the system, kind of XDP adjacent related, but understanding that jitter so that we can ensure that we can have a consistent performance of our XDP code. Again, we look at things like frame graphs or code annotations. We're looking at averages, so it doesn't necessarily encompass the variation. So taking this to the next level to be able to see that variation so that we can kind of control that and be able to increase our quoted max packet rate. We also have tools from the BPF compiler collection that can help look into this and provide histograms, which provide some more enriched data for that understanding. Also, I've been trying to understand or trying to think of ways to build a visualization for the instruction level sampling. In the same way that kind of flame graphs provides a high density image for call graphs, is there some way that we can do that with the code annotations as well? And also last year, Facebook added a consumer producer test harness that allows for multiple consumers and or multiple producers. This would allow, as I mentioned, the MicroBenchmarks today is a single consumer producer, so we're only looking at path length costs without the contention. Here, this harness that they have added to the kernel allows for us to build more robust benchmarks so that we can not just look at path length, but also simulate various contention targets to further enhance our ability to understand the data structures and help decide when to use them. So again, we were reminded of the importance of active benchmarking, ran into several interest and observations that we were able to gain insight into and mitigate and work around. We demonstrated how, with our approach for performance analysis, how we can use existing tools and new tools in our approach and be able to continue to make informed decisions to improve our code. And lastly, we hope that this encourages others to get into doing XDP and BPF analysis. The BPF is a rapidly growing area of the Linux kernel, and I believe it's a key factor to its continued adoption is for it to have good performance. And as we build more complex code, the need to do that analysis becomes critical to maintain that performance. So with that, I thank you for attending, and at this point, be willing to answer any questions that you have. Thanks again.